That's how you maintain greater intracellular concentration of potassium. Okay? So what do we do here? We need to send this back to circulatory system. Okay? So I need to send this to blood. This is where you have your blood, right? So what do I need to do to make this happen? You get to use also specialized channels, protein channels, that work with chloride. So there is something called chloride shift, where chloride is coming in, and then bicarbonate is going out. So you get to do this. Chloride in, both negatively charged, by the way. See that? Now you have your bicarbonate in your blood. Where can it go? Bile, right? Pancreas, liver make bile, and you store it in gallbladder. One of the ingredients that you will find in bile is bicarbonate. That's how you get to neutralize hydrochloric acid of the stomach at duodenal level, right? Because when you enjoy that triple whopper, that's a lot of hydrochloric acid to break that down, right? So what happens is that little by little, through caloric sphincter, you allow some of that chyme, that is food plus hydrochloric acid, to enter duodenum, and then at that level, your biliary duct will allow bile. So this goes to and becomes part of bile to manage the chemistry of the body, neutralizing hydrochloric acid. Make sense? So now we can see the role of three body systems handling three major players in this buffer system game involving hydrogen ion, carbon dioxide, and bicarbonates.
So the renal and the digestive system work together as...
All of them. I'm breaking it down. Remember that.
Okay.
All of your body systems are connected.
Okay,
So it's a systemic approach. I'm just breaking it down. The laziest one out of three is renal. Because it takes days for the renal system to respond and try to compensate. And so it's just kind of a effective but lazy, slow to respond. So it takes days, whereas respiratory is immediate almost. Right? So any other questions? So then, these three are important focus for us to understand how our body is capable of handling the fluctuations in the pH. Right? So now, if you come back to your arterial blood gas values, you can do the same thing. First thing I do, I look at my pH. And that will tell you you have two possibilities other than being normal. You either have acidosis or you have alkalosis. We learned that we looked at CO2. Now we're going to look at exact same thing. So if your pH says that it is alkalosis, and then this is alkaline, right? Just making sure. So if you have too much of this, the environment is, so your pH is alkalosis, and you have increased values for bicarbonate, that means they both are saying alkalosis, and you already know it's alkalosis, but the cause is metabolic. You see how that works? So this will tell you metabolic, this will tell you respiratory, this will tell you acidosis, alkalosis. Yes? It would be great if everybody agrees on the same thing, but sometimes they don't. That's just like, oh my God, now what? So that's where you kind of justify things, okay? And in your handout, at the bottom of that page, I have Rome, R-O-M-E. You see that?
Yep.
So you have R-O and M-E basically. What does it say? It's respiratory, and then metabolic. So what it means really is that respiratory can be opposite of bicarbonate. So they may have opposite values in terms of pH. What does that mean? So first things first, you look at your pH, and we're going to practice that. You look at your pH, and that tells you only two things. Based on your values, your diagnosis is either alkalosis or acidosis. You're done with that part. Now you move to the second part, CO2. CO2 agrees, good, no problem, so you will say, okay, acidosis or alkalosis, but respiratory cause. If bicarbonate is agreeing with pH, whether it's alkalosis or acidosis, that's metabolic-based alkalosis, acidosis. But what if pH says acidosis, CO2 says acidosis, bicarbonate says alkalosis? Then you flip a coin. No, you don't. So what happens is that your body is saying, I'm suffering from respiratory acidosis, but my body is trying to compensate and solve that problem through metabolic activities. So you're compensating. So diagnosis is compensated respiratory acidosis, where pH says acidosis, CO2 says acidosis, but you have the opposite value for bicarbonate. That means your body is saying, I am suffering from respiratory acidosis, but my metabolic aspect of my body is trying to solve that. That's what it means. So when you have compensation, that means there is disagreement. If that disagreement is coming from bicarbonate, right, that's true compensation, because that's a very strong response. So if it's compensated, you will see the opposite value of bicarbonate to these two. That's compensation. Either way, acidosis, alkalosis. If you see these two are agreeing, but this is disagreeing, that means you're trying to use respiratory system to compensate, and that's a weak system to respond, therefore that is called partial compensation. So I'm going to wrap it up and then have you make diagnosis. Metabolic, complete compensation. Respiratory is agreeing, partial compensation, and if everything's agreeing, there is no compensation, so everything's saying the same thing. Questions about that? Chloe?
If someone if they're compensating metabolically, does that mean that they've been in this for a long time, since you said that renal is slow to respond?
Yeah. And then you go by values also.
Okay.
The severity and the numbers. What is? So because this is pretty much, you will see it plus or minus 2. Something like that. So your value is going to fluctuate like that. If you see extreme, then whichever is the strongest will tell you So the range of change here versus here, compared to that, will give you some clues in that aspect. Everybody's okay? Now, look at your handout. You have 5 cases. Go ahead and make your diagnosis. First, you look at pH, then you look at your CO2, then bicarbonate, and then make diagnosis. Let's do that.